In the last class, we were discussing about the diode characteristics. We have seen how the diffusion of holes from the n side, from the p side into the n side, and the diffusion of the electrons from the n side into the onto the p side, and contribute for a huge amount of current when the diode is forward biased. And as a result, when the diode is forward biased with a very small voltage drop across the diode allows a huge amount of current. These injected carriers, which were the majority carriers on either side, say for example the holes on the p side, after getting injected into the n type, so there they become minority carriers, huge amount of minority carriers, and these are now drifted by applying the external potential. By the external the field due to the external potential drifts these minority carriers. After diffusion they become minority carriers on the other side, and they are drifted by the field, and as a result there will be huge amount of current. Well, on the other side, when we apply the reverse potential, the current is only due to the minority carriers. And in the example which we have taken earlier, when the doping profile is doping concentration is 10,000 times more than the intrinsic carrier concentration, we found that the majority carrier concentration is of the order of 10 to the power of 13, whereas the minority carrier concentration is of the order of 10 to the power of 7. Therefore, the current ratios would be in that order. So if the in the forward direction the current is very high, in the reverse direction the current would be very small. Okay. Therefore, the diode acts like almost like an open circuit, because it allows only a very small amount of current, which is of the order of 1 nanoampere in the case of silicon diodes. Okay. Now let us continue the discussion and look at this plot. So typically, this is the plot of a diode with, if it is a silicon diode at above 0.6 volts, with a small increase in the voltage across it, the current increases, whereas in the reverse direction here, up to a high amount of voltage, depending on the construction, it may be 10 volts or 20 volts or 5 volts, the diode breaks down, and so there would be a huge amount of current again. So this is the characteristics of the diode, of a typical diode, with the volt ampere relationship given in this fashion. Now, when temperature rises, we have seen that with temperature this I naught varies. I naught is a function of the temperature, absolute temperature. So that means with temperature we expect the reverse saturation current to vary, and thereby the voltage current relationship also to vary with temperature. And please note that here itself we have a huge amount of temperature variation, maybe from 7 to 8 degrees Celsius to about 45 degrees Celsius is the variation. And if you go to polar regions and bipolar regions, thickly habitated regions like the northern areas, the temperature goes down to sub-0 degrees Celsius. And if the electronics is being used in an industry where the furnace heating is present, the temperature may be as high as even 50 degrees centigrade, and very close to the furnaces it may go even further up. So because of such a huge variation in temperature, it is important that the electronic circuits also work properly. And if the temperature is limited by the manufacturer for an electronic circuit, like some computers earlier, so we were saying that these computers require air conditioning. They work only in an air conditioned environment. So when the air conditioning is not present, because of power dissipation, there would be a lot of temperature rise and the circuit may not behave properly. So this kind of restrictions keep coming in unless you design a circuit to work in varied temperature environments. So it is important that the circuits work at different temperatures. Now let us see this simple device like a diode, how its characteristics varies with temperature. I naught, the reverse saturation current, so gets doubled for every 10 degrees centigrade rise in temperature, or it varies by 7% for 1 degree rise, 1 degree centigrade rise in temperature. That is a huge amount. That means the reverse saturation current is highly sensitive to temperature. Now with this kind of variation, so you will find that the volt ampere characteristics also varies like this. If this is the case at say 25 degrees centigrade, so the characteristics may be like this at say minus 50 degrees centigrade, and at higher temperature than this the characteristics goes up like this, like at 150 degrees centigrade. So this is the characteristics for the diode. So this is how the temperature varies. So if you substitute this variation in of I naught, that means doubling for every 10 degrees centigrade rise. If you substitute in the expression above, you will find this difference. For instance, if I give you the voltage as V as say 0.65 volts and I naught as 1 nanoampere, and you know that Vt is of the order of 26 millivolts, and eta is equal to 2 for silicon, you can find out how much is the current corresponding to 0.65 volts of voltage applied across it. Now if the temperature is raised from say 25 degrees centigrade to say 55 degrees centigrade, then I naught would be, instead of 1 nanoampere here, it will be 4 times now, because the increase in the temperature is 2 decades, is by 2 decades. Therefore, the I naught would be 4 nanoamperes. So with 4 nanoamperes you can find out how much is the rise in the current I. So it would also be of the order of 4 times. Okay, so this is what happens with rising temperature. Any questions on the diode characteristics and its?
So the breakdown voltage increases or decreases with temperature?
There won't be an appreciable change in the breakdown potential because of the difference in the whole electron pair, intrinsically generated whole electron pair, there would be a small amount of minority charge carrier variation. This is one. And number two, the energy band gap also changes with temperature, slightly varies with temperature, because of which there would be some amount of change in the breakdown potential. So, but then it is not appreciable. It's not much. Any other question?
So, is there a mathematical formula for the I naught?
Yes, there is a mathematical formula for I naught in terms of the diffusion constant, mobility, etc. There is a formula, and there is a derivation through which it can be arrived at. So, since it is beyond the purview of your class, that is not done here. It is available in the textbooks which are whose list is given to you. With this, now let us take up the diode circuits. So now we are coming to the application of diode. So let us consider a diode in a simple circuit like this, a simple circuit with a single loop. So let us consider, let us use a diode here and a load resistance, and let us apply some excitation or apply some voltage here, and this is the load resistance RL. It's a very simple circuit. And what kind of voltage we get across the load resistance? So this may be a motor or it may be a bulb, okay, for which the voltage is passing through the diode. Okay, so load resistance means something like that, some utility equipment which loads the supply, and we are using a diode in the circuit here, right? Typically such loads are resistive by nature, whose volt ampere relationship is governed by the Ohm's law. So let us consider a simple load resistance RL and look at the circuit, what happens here. If you apply Kirchhoff's voltage law here, and the voltage drop across the diode is Vd, so by the relationship, and if the current passing through is I, then the Kirchhoff's voltage law says that Vi is equal to, so Vd plus IRL. So this is one equation. Applying Vi, we are interested in finding out V naught or the current. Now here we have two variables, Vd and I, two variables. Vi is given and RL is given. We are interested in finding out I. How do we solve this? Well, Vd and I are related by this function here. Look at this. So this is the function which governs Vd and I. The mathematical expression for this is this. I used the symbol Vd there and I used V here, but both are same. Please note that both are same. So this is the relationship. So I is a function of V. So that is given by the diode characteristics. Now how do you determine? So that is one equation. So Vd is a function of, or I is a function of Vd, and the function is known. It is known graphically by the characteristics. It is known mathematically by that exponential equation. Now that is the second equation, and this is the first equation. Now solving these two equations, we can find out for a given Vi and for a given RL, how much of I would be the resulting and how much would be Vd. So we have to solve these two equations. How to do it graphically? Given a characteristics, we can do it graphically. When two equations are given to you and you are asked to find out the point for which these two equations are valid, so you know that the point of intersection is the solution of the equation. So now we have one equation given here, BD as a function of I, and now let us draw the other equation also on this, plot the other equation also on this, and the intersection point will give us the solution VD and I at which the diode is operating. So now this equation is, in terms of VD and I, please note that this is a straight line equation in terms of VD and I. So this equation, so when plotted it would be like this. This is a straight line equation and this is a straight line, and VD is equal to VI when I is equal to 0. This is the I axis when I is equal to 0. So VD is equal to VI is 1 point. So VI 0 is 1 point on the straight line, and VI by RL is the other point on the straight line. 0 and VI by RL is the other point on the straight line. So what is the operating point? Naturally, so this is the operating point. So then this diode works with this particular VD and this particular I. So this is the operating point. I repeat, we have found this by solving these two equations, and that is done graphically here. So this is a straight line equation governed by Vi is equal to Vd plus IRL, that equation, and this is the I is equal to f of Vd. This is this plot. This f is that exponential equation which I have given in the given previously. So now this is the operating point. So once you know I and once you know Vd, from the first equation we can find out how much output voltage we get. So this is one way of determining the currents and the voltages when you use such a nonlinear device like this diode in circuits. Well, this is a graphical method. So mathematical method is another method which is straightforward. So that can be obtained by solving this equation and the exponential equation. Okay, so this can also be used. So this line is known as load line because it depends on RL. The slope of this line is minus 1 by RL. It depends on the load resistance, therefore it is known as load line, and this can be used to determine the operating point. There is another very interesting way of analyzing active circuits involving an active device like a diode. So that is by piecewise linearization of the characteristics. So the characteristics of the diode can be so represented by this kind of piecewise linear characteristics, whereas the actual characteristics is like this. So whereas the actual characteristics is by this dotted red line, we can make it piecewise linear with the objective of representing it by linear equations to make it piecewise linear, and with this voltage given by the cut-in voltage, and with this obtained by the slope of the characteristics, diode characteristics. So by first expressing it in this kind of piecewise linear characteristics and representing it by an equivalent circuit. Let us see what is the equivalent circuit of the diode after this piecewise linearization. Without piecewise linearization, it is a nonlinear device, and you cannot represent it by voltage sources, resistances, etc. Now, once you linearize it, so you can represent it by resistances and voltage sources. For instance, you take this branch of the characteristics with this line. Let me reproduce it here. So with this line, this line. How do you represent this? What kind of circuit yields you so this kind of characteristics? Don't you think a resistance in series with a source with V gamma so gives you this kind of characteristics? When the applied voltage Vi is more than V gamma, what kind of current flows through this circuit? What is the current flowing through this circuit? I is equal to Vi minus V gamma by R. Don't you think this characteristics is that if V is this, if this is V, if this is V gamma, so don't you think the current that is flowing through is proportional to V minus V gamma? Because this equation is a straight line. Hence, so this equation can be represented by this kind of expression. And what kind of circuit exhibits this kind of expression? So this circuit exhibits this kind of expression. Of course, this is valid when Vi is V more than V gamma. So this is valid when Vi is beyond V gamma, when Vi is more than V gamma. So when Vi is more than V gamma here, so this is Vi, so then the relationship is linear relationship like this. With the slope of the curve given by 1 by R. So the slope is 1 by R. It is very interesting. First, the characteristics is linearized by an approximate linear function, and we have written down an equation for it. So the equation is something like this. So Vi minus V gamma divided by something like a resistance is with some term with units as resistance is giving rise to the current I. Okay, so therefore this is the equation of this line. What is the circuit equivalent for this? So this is the circuit equivalent for this. So this kind of circuit gives you this kind of equation. Hence, the diode can be approximated to this kind of circuit when the input voltage is more than V gamma. That is the interesting conclusion from this. It is an approximation, no doubt. But please note that that approximation is very closely valid, because these characteristics can be very closely approximated by this linear equation. Right? So this is, I repeat, is applicable for Vi greater than V gamma. Well, when Vi is less than V gamma, what is the characteristics? So when Vi is less than V gamma, the characteristics can be approximated by another straight line whose slope is very small. Please note that, so this characteristics can be approximated by a function, a straight line of this type. So this is valid up to V gamma. So beyond that it is represented by this straight line. And on the negative side, up to what voltage this is applicable? Up to a voltage of Vz, that breakdown potential. So this is applicable. So that means, so when Vz is less than or equal to Vi less than or equal to V gamma, so this is the straight line equation. The diode characteristics can be approximated by this straight line equation. So it is a straight line equation between voltage and current passing through the origin. So what is it? What kind of circuit element gives you this kind of characteristics? Simply a resistance. So a diode can be represented by a simple resistance. And this resistance, is it same as the previous resistance? So this resistance value is very large, because for a huge amount of voltage the current is very small. So this is applicable under reverse bias, therefore this can be represented by RR. The small r indicates, the suffix R indicates under reverse bias. So this is the equivalent circuit of the resistance under reverse direction. And to indicate in the resistance in the forward direction, so let us indicate it by RF in the equivalent circuit. Hence, the diode can be represented by a resistance in series with a voltage, a resistance RF in series with a voltage source whose value equal to V gamma, as long as the input voltage is greater than V gamma. And it can be represented by a simple resistance of a large value, that is RR, when the input voltage is less than V gamma and of course more than that Vz, the breakdown potential, which is negative. Okay. So what we have done now is simply represented a diode by a simple circuit. Well, we don't have single circuit representing the diode, but depending on the input voltage applied, we have two different circuits that are applicable. Well, this is good enough for most of our purposes, I mean, our analytical and design purposes. Any questions on the equivalent circuit of the diode? The objective is clear. The objective is to analyze the circuits and find out for a given voltage how much of current flows through, etc. So to do that kind of analysis and design, we need this equivalent circuit. Yes, there is a doubt. Because it is not a passive element like a resistance or inductor or a capacitance, where the applied voltage and current relationship is a passive relationship. Here you have some kind of nonlinear relationship which depends on the operating point. What is the background voltage you have applied and what is the background current you are operating it at. So depending on that, its characteristics changes, therefore it is known as an active element. Plus it does some active functions for us like rectification and things like that. So that's why it is called an active device. A transistor is an active device, a diode is an active device, and so on. Any other question? Well, let us see under the breakdown conditions what is the equivalent circuit. It is interesting to know because we do operate the diodes in the breakdown region also. There are some very interesting applications where we operate the diode in the breakdown region. So let us see in the piecewise characteristics. Here you have this kind of characteristics. If you neglect the current, reverse saturation current, so this is the equivalent circuit. So voltage, current, and this is the equivalent circuit. So for this is Vz and Vi is less than Vz, like this. When Vi is like this, what happens to the diode? It gives you a large amount of reverse current for a particular Vi. And now how do you represent it? So this can be represented by, or the current flowing is, so Vi minus mod Vz, right, Vi minus mod Vz divided by something which has units of resistance, let us call it as Rz. So that is the current that is flowing in the opposite direction. So let me use this as IR as Vi minus mod Vz by Rz. This is the expression. Okay. So this can also be represented by, in the reverse direction, if you reverse the diode now, and express it, so you will find that, so this is also equivalent to a voltage source in series with a small resistance Rz, which is very small, and this voltage is Vj, so which is positive, so that is why I am representing as mod Vz. If this is the voltage applied, but this voltage applied is a reverse voltage. If this is Vi with this side positive and this side negative, when this Vi is more than Vz in the reverse direction, so it allows a large amount of current, and that current is Vi minus Vz by Rz. That kind of current flows. This is minus IR. Okay. What is the value of Rz here? What is the order of magnitude? It is very small. It may be a tenth of an ohm or a fraction of an ohm. Now let me discuss about rectifiers. Rectification is a very important application of diodes. Okay, I started discussing about diode as a circuit element. Diode as a circuit element, an important application where diode is used as a circuit element is rectifiers. And rectifiers are very popularly used in power supplies of electronic circuits and many other kinds of circuits, or even electromechanical devices. We use rectifiers as the power source to convert an alternating voltage into a direct voltage form. Let us see how the diode acts like a rectifier. So we use a diode and the load resistance which we drive is connected in series with the diode, and we apply an alternating voltage here. The alternating voltage is usually a sinusoidal voltage with 50 hertz as the frequency in our country. This is the way the voltage varies with time. So, with this kind of voltage applied to the circuit, to the load which is being driven by this kind of alternating voltage, when this diode is being used as a series element, so what kind of output voltage do you get? So, we find that the output voltage we get is a rectified voltage of this type. With respect to time. So, the diode clips the negative portion of negative half cycle of a sine wave, and it allows only the positive voltage to pass from the input side to the load resistance. So, this kind of operation is known as rectification. It rectifies the negative portion, it clips the negative portion and makes the voltage a positive voltage or a negative voltage if you reverse the terminals. Okay. So, this application is known as rectification. How does it do this? So, this is the output voltage as a function of time. Since the diode acts like, except for that small voltage V gamma drop in this and an additional voltage drop, at the most how much voltage gets dropped across the diode for an appreciable amount of current? 0.6, 0.7, 0.8 at the most. Okay. With 0.8 volts drop across itself, it allows rest of the input applied voltage to appear across RL, because it is by Kirchhoff's voltage law, voltage drop across the diode plus load voltage is equal to applied voltage. Say you have applied say 100 volts at the input, some 0.7 or 0.8 volts drops across the diode, and remaining almost 99, the remaining say 99.2 volts drop across the load resistance. That means the input voltage is allowed to pass to the output. Okay. So, the diode allows it to pass through, whereas in the reverse direction, for this large amount of reverse potential for during the negative half cycle, so because of the large amount of reverse potential across the diode, some current flows, but that current is the reverse saturation current. As long as this reverse voltage does not go beyond that breakdown voltage, as long as this voltage is less than the breakdown voltage, the what is allowed by the diode is that reverse saturation current, which is of the order of 1 nanoampere in the case of silicon diode. So, with 1 nanoampere current that is passed to the load, it is a negligible amount of current passed to the load. It is almost that no current is passing to the load. As a result, the voltage drop across the load would be almost 0, whereas the entire voltage that is applied here, the reverse voltage, drops across the diode, and because the current is very small, so there is almost no voltage drops across this load resistance. Hence, the output voltage across the load would be of this type. Positive voltage is allowed to pass to the load, and the negative voltage is almost negligibly small. And during the next positive half cycle, again the diode conducts, it allows the current to pass through, and the voltage goes to the load. So that's how a rectifier works. And with negligible voltage drop across the diode, and ideally speaking, now let us see what is the characteristics of an ideal rectifier. So if we want the diode to act like an ideal rectifier, so what type of characteristics do you expect? So for positive half cycles, do you expect zero resistance and zero voltage to drop across the diode, and the whole voltage is passed to the load? And during the negative half cycle, so you expect the diode to offer infinite resistance and do not allow any current to pass through. So ideally the diode, a rectifying diode characteristic should be like this. So like this. So this is voltage, so this is current, okay. This is voltage, this is current, the characteristics is like this. For positive voltage, even with zero voltage, it should allow current to pass through. For negative voltage, with any amount of negative voltage, the current that is passed through is zero. So this is the idealized characteristics or characteristics of an ideal rectifying diode. So when the diode is ideal, if the input voltage is an alternating voltage, so which is equal to, so let me say that the voltage is, peak voltage is Vm, and it is a sinusoidal expression, sin omega 0 t, where omega 0 is the radiant frequency of the sinusoid, which is equal to 2 pi into 50 hertz, which is equal to 100 pi radians per second in our country. In some western countries like US, 60 hertz is used, so where it is 120 pi radians per second. So this is the expression for the input voltage, where Vm is the peak voltage. When sin omega naught t is a multiple of pi by 2 and 3 pi by 2 and so on, so you have the peak voltage, so peak voltage is Vm, okay, at 0, pi, 2 pi, etc., so it is 0. So with Vm as the peak voltage here, here, if this is applied and the diode is ideal, so what would be the output voltage, peak voltage? The output would be a half sinusoid during every cycle, and the peak voltage is Vm itself, because the voltage drop across the diode is, an ideal diode is 0. Therefore, Vm is the voltage drop. So this kind of a rectifier is known as a half wave rectifier. So it rectifies and produces only half wave in the output. For every one cycle, you have half of the cycle present, positive half of the cycle present. Okay? Therefore, it is known as a half wave rectifier. Well, so now the rectified voltage is like this. So it doesn't go negative, it is only positive like this. Is it this kind of voltage that is needed in some circuits or some devices? We want constant voltage to operate some devices like electronic circuits, like I say transistor radio, okay, or television. So there we want constant voltage, in which case this simple half wave rectified voltage is not sufficient. Well, if you look at the half wave rectified voltage waveform, So, which is like this. So, this can be expressed as some constant voltage plus some varying voltage. So, please look at this. Can't this output voltage, rectified voltage, be written as sum of, so this constant voltage and this time varying voltage? If you find the average of this waveform, so this is the average plus some alternating component with 0 average. So, this can be expressed in this form. That means this voltage has some constant in it plus some alternative, positive going and negative going, some alternating component in it. So, definitely this has some direct voltage, DC voltage with some alternating component. Now, our objective is to reduce this component as far as possible and to retain this. What is this DC voltage I am talking about? It is naturally the average of this waveform, and if you apply this voltage to a DC voltmeter, so DC voltmeter, so what this voltmeter reads, so that is the DC voltage. A DC voltmeter gives you the average of this. So, that is what the DC component of that, and that is this one. It has an alternating component which goes positive and negative, that is this component. So, this is the AC component. So, this is wanted and this is unwanted when you use this as a circuit element.